We want two cards of the same suit, right? So what that's saying, and this is kind of like a hidden or situation, right? It's saying find the probability of getting a heart and a heart, or a diamond and a diamond. Poor quality diamond, but gonna live with that. Or a club and a club, or a spade and a spade. Upside down heart with a stem. Upside down heart with a stem. All right, so these are our four different scenarios. Now, the probability of getting a heart is 13 out of 52 because a quarter of the deck, there's 52 cards in the deck, a quarter of the deck is hearts, a quarter is diamonds, and so on. All right, so 13 out of 52 would be the probability of getting a single heart selected at random. All right, so you get a 1 in 4 chance of the card you selecting being a heart. All right, but unsimplified, that's 13 out of 52. If I'm lucky, which I guess wouldn't require too much luck, but if I end up getting a heart, then I don't replace that card before selecting another card, the probability of getting a second heart would be, well, now there's one less heart in the deck. There's also one less card overall. So 12 out of 51, which would be 156 over 2652. All right. And so kind of along the lines of what we were talking about yesterday, we want to start looking for the, kind of the shortcut through the maze. We don't want to have to figure out each probability associated with each different alternative. If we know that they're going to amount to the same thing, then why not just take this and multiply it by 4? All right? Because if you were to reset the deck, the probability of getting a diamond, it's still a quarter of the deck. It's still 13 out of 52. If you select one of the cards at random and it turns out that it's a diamond, there's going to be one less diamond, bringing you down to 12. There's going to be one less card, bringing you down to 51, which would, again, give you 156 out of 2652, and that would be the same for the clubs and the spades. All right. So then it's just a matter of multiplying 156 by 4, which I think is, 624, over 2652. 2652. And that would be your probability. All right, so if you wanted to, you could just kind of have a quick look at that in the calculator. So 624, they're just simple computations, so you don't need anything fancy for it. It's not quite 25%, but it's in the neighborhood. All right, so if whatever the game is playing required me to have 2 cards of the same suit in order to win, this would be my chances of winning.
How do we know to only multiply the numerator?
Because when you multiply by 4, that's the same as multiplying by 4 over 1.
Oh, okay.
Right. Now, number 4 is just kind of a more intense version of number 3, although it's the same skill. So once you figure out, like I said, the shortcut through the maze, you're good. 2 cards of the same value. All right. One assumption that we have to make is that 2 cards will have the same value regardless of whether it's a number or a letter. All right. So all twos are equivalent, all 3s are equivalent, and so on. But all jacks are equivalent to one another, all queens, all kings, all aces. They don't have numerical values, but they do have an intrinsic value. So I'm looking for the probability of 2 and a 2, or probability of 3 and a 3, or probability of 4 and a 4, or 5 and a 5, 6 and a 6, 7 and a 7, 8 and a 8, 9 and a 9, 10 and a 10, jack and a jack, queen and a queen, king and a king, all the way up to ace and an ace. All right. We don't want to have to write out all of that, because if it follows the same concept of number 3, then it's just a matter of multiplying. Figure out the probability of one single event, the event of getting a 2 and a 2 specifically, and then multiply it by the number of possible pairings that you could have. Now, if you counted them all up as I was rattling it all off, you'd see that there are 13 possible pairings. All right, so 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. All right, so figure out the probability of getting a 2 and a 2. There's 4 2s in the deck out of 52 overall. Select one at random. It turns out that there's a 2. You got a 2. You got lucky. It was a 2. There's one less 2 in the deck. There's one less card in the deck. That gives you 12 out of 2652. Since there's 13 possible pairings, we would then multiply this by 13, and we get 156 out of 2652. Which is kind of an interesting outcome. That is all. I have nothing to elaborate on that. No, we got 156 over 2652 over here. And that was just a single circumstance of getting 2 cards with the same suit. So a heart and a heart, for example. All right. So it's just as likely to get 2 cards of the same, 2 cards of a particular suit, not the same suit, but a particular suit, like just a heart and a heart, or just a spade and a spade, or whatever. It's just as likely to get that as it is to get any pair of identical values. It's just kind of interesting.
So is that just like because there's like 13 individual values and each suit has 13?
Exactly. It's pairs involving 13 possibilities versus, well, I don't know what the word would be for 13s, like pairs becoming 13, so like a group of 13 involving 4 possibilities.
Yeah.
So,
That's cool. Coincidence.
yeah. Now, we want some shortcuts. We don't want to have to do the lengthy stuff all the time, but sometimes you're stuck with it. So we get to an application of general multiplication rule. This idea is at least 1 is equal to 1 minus the probability of none, or the probability of at least 1. That's pretty dark, actually. Hold on, let me clean that up. All right. So, and at least 1 is 1 or more. I think most people know that, but just in case. So this is kind of a cool outcome, but we're going to expand upon this as we go forward, because it isn't always just going to be at least 1. It might be, you need the probability of at least 10 or at least 5 or something like that. All right. So when they say find the probability of tossing at least 1 heads in 2 tosses of a fair coin, there's a few different ways to handle it. One way would be to make a tree diagram or list a sample space, which wouldn't really be difficult. Because if I'm tossing a coin twice, I could look at it and say, heads, heads. Those are my two possible outcomes. Heads, tails, tails, heads, or tails, tails. All right, so each pair of outcomes combined together give me my sample space. All right. So at least 1 heads in any of these possible pairings would happen 3 out of the 4 times. This chair is squeaking like crazy. It's annoying me. I need to get some WD-40 on it or something. So 3 out of the 4 instances here involve at least 1 heads. So the probability of getting at least 1 heads would be 3 out of the 4 possible arrangements of heads and tails. All right. Now we could also look at it a different way. What if I wanted to find the probability of not getting heads at all? All right. So what I could do is find the probability of getting no heads. Now, since we're tossing a coin twice, that would be the same as saying find the probability of getting a tails and a tails. Now, flipping a coin, those are independent events. So having one outcome would be unrelated to having another outcome. So it's not like the cards where you have to worry about replacing it. You're always going to have two sides of a coin, assuming it's a fair coin, one of which will be heads and one of which will be tails. So that'll keep the probabilities consistent.
When we're like writing out like the P, for instance, whatever, is there any way we could like abbreviate that? Like if we just, for the P of at least one head, could we do like equal to or greater than one head?
Yeah.
Okay.
So probability of tails and tails with independent events, we would just say it's the product of probability of tails and probability of tails. We don't have to worry about the given stuff because it doesn't matter what came before it. The probability of getting tails is always going to be the same. All right. I could say the probability of getting, for the second event, I could say the probability of getting tails given that the first outcome was a tails, but since that's not going to impact the probability, what's the point? All right. In the case of drawing cards from a deck, it made more sense to write it out that way. But even that we kind of got lazy on. And by we, I mean me. So 1/2 times 1/2 would be 1/4. That would be the probability of not getting heads at all. All right? Probability of getting tails, which is the exact opposite of the thing that we would want. Now, if we know that complements in probabilities add up to 1, and complements are opposite events, then all we would have to do to find the probability of getting at least one heads is subtract this number from 1. And the result would be what we got before when we did it out by listing the entire sample space. Now, you could probably already see a drawback to this approach. Sorry, this approach. And that is, if you can't easily list the sample space, then how are you going to come up with the probability based off of the sample space? All right, so you need a formulaic approach in most cases in order to figure these probabilities out, because it will get out of hand. I can show you for 3 tosses of a fair coin, probability of getting at least one head. I mean, we could still list it out, but the sample space is a lot longer. It's double the length. Okay, so relatively speaking, it's a lot longer. So heads, heads, tails, heads, tails, heads, tails, heads, heads, and we'd have tails, 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 heads, tails, heads, tails, and heads, tails, tails. All right, so that would be the complete sample space for 3 tosses of a fair coin. Now we want to know the probability of tossing at least one heads. So that would be, well, we got at least one heads there, 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 not there, 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 there. Probability of tossing at least one heads. I just did a copy-paste job here, but I'm obviously going to change it because it's not the same solution. But if we wanted to do it using this complement rule, what we would do is find the probability of getting no heads in 3 tosses of a fair coin. All right, and so from there, we start kind of streamlining the process, which is going to really help out a lot, because probability of getting tails and tails and tails, still not too difficult. You're just multiplying by another 1/2, which is going to give you a 1/8. 1 minus 1/8 is going to give you a 7/8. But then you get to the whole point of this progression here. Find the probability of tossing at least one heads in 37 tosses of a fair coin. Right? So you're not making a sample space for that. But the idea is hopefully we'll have learned from this process to be able to come up with a solution, right, without having to try to list the sample space. Now, just to even streamline this further, probability of tails times probability of tails times probability of tails really can be thought of as probability of tails raised to the third power. All right, which in turn gave us 1/2 raised to the third power, but that's almost irrelevant because it's the preceding computation that really gets the job done. All right, so what this actually ended up being as a rule would have been 1 minus the probability of tails to the third power. All right, so expanding that to number 3, we could say, all right, well, it's not 3 tosses of a coin, it's 37 tosses of a coin. So the probability of at least 1 heads would be 1 minus the probability of getting a tails raised to the 37th power. All right, so 1 minus 1/2 to the 37th power. And sometimes, when the power, you've worked with exponential functions before, when you deal with high enough powers, sometimes you get an overflow in a calculator, so you just got to be careful about that, but we can give it a shot. 1 minus 1/2, or 0.5 if it's more convenient to type it in that way, raised to the 37th power, and we get that. All right, if you over-round it, it's going to go to 1, so you're just better off putting that whole decimal in there or leaving it in fraction form. All right, so because even if you tried to get a common denominator and simplify it, 2 raised to the 37th power is going to be that. I mean, it's just not practical. All right, so either you're writing that entire decimal or you're just leaving it in this exponential form. So I'm going to go cross-eyed here trying to read it, but 6 9 11 nines. All right. So then a die is rolled 6 times. Find the probability of getting. Oh, sorry. A die is rolled 6 times. Find the probability of rolling at least 1 4. All right. So we change the context here a little bit. If you roll a die once, there's 6 outcomes. Twice, there's 36 outcomes. I already wouldn't want to list the sample space, but 3 times there'd be 216 outcomes. I believe 1,296 for 4 rolls of a die. It gets crazy. All right. So I think there's 7,776 for 6 rolls of a die, but I'm not 100% sure. That might be 5. Let me see. To the 6th power. Oh yeah, so not even close. Yeah, it was the 5th power. Off by a power of 6. What a world. Anyway, so I would want to use this idea here. So I can't say the probability of getting tails, but I can use the same structure. Probability of at least 1 4 would be 1 minus the probability of, well, again, not tails, but it's going to happen 6 times, so whatever I put in there is going to be raised to the 6th power. So the argument here is the number 4. The argument here was heads. All right. In the solution, we use the opposite of the argument in the original probability expression. So whatever this is, we use the opposite here. All right. So at least 1 4, 4 being the argument, I need the opposite of 4. And in a normal mathematical world, we would say -4, but that doesn't make sense contextually. So we would say anything but a 4. All right. So if you're rolling a die, and I say I want the probability of not getting a 4, I'm really saying the probability of getting a 1, 2, 3, 5, or 6. So anything but a 4. So instead of writing 1 or 2 or 3 or 5 or 6, I'll just use a not symbol and put a 4. All right. So not 4, a little tilde. Swinton. So probability of not getting a 4, when you roll a die, 5 out of 6 probability, because there's a 1 in 6 probability of getting a 4 when you roll a die. All right, so 5 out of 6 raised to the 6th power, subtracted from 1. By taking 5 over 6 and raising it to the 6th power, we're coming up with the probability of the thing that, the one instance that we don't want, or the quote unquote one instance that we don't want. And so by subtracting that from 1, we'll get the probability of the thing that we do want. All right, so computationally, at least in decimal form, pretty hideous. So 1 minus 5 over 6 to the 6 is about, so approximately 0.665. All right, in Desmos, they'll give you the little fraction converter, so that's kind of nice. But we can't count on that with a TI. So if you want to do it with a TI, you'd need a common denominator, right? So, but that's not too bad, because all I would really do here is raise my 5 over 6. I'd raise that, each part of it, to the 6th power. So I'd do 5 to the 6th, and then 6 to the 6th. All right. So if I needed to figure, for whatever reason, if I needed to get it into simplest fraction form, or any kind of fraction form, I'd make the 5 over 6 to the 6th power into its fractional equivalent. Well, it's already a fraction, but, without a power. That 1, I'd write that as 46656 over itself, and then just do the subtraction, right? Because 1 is really any number over itself, and so I want that number to be the other fraction's denominator, just so I have that common denominator. Carry out that subtraction, and we'll get 31,031 over 46,656.
I think you switched the 5 and the 2.
I think you may be right, and by maybe I mean definitely.
Where'd you get the 1, 5, 6, 5, 3, 5?
Yeah, just raising the 5 to the 6th power. So we evaluated it by taking each part of this fraction, raising it to the 6th power. All right, so that's a good chunk of multiplication rule. The last application, or at least in simple probability, everything is considered simple probability so far, which is really depressing. If you were like me when you first were exposed to a lot of these probability concepts, and you're like, it doesn't seem very simple, especially those side examples we did yesterday. Like they can get pretty complicated. Simple just means that you're applying simple arithmetic to determine the probabilities. You don't have to use any kind of crazy functions. But contingency tables are the next application, and they're, practically speaking, pretty easy to do. But in terms of the genesis of it, it's kind of strange. It's actually originating from the general multiplication rule, because if we start off with the probability of A and B being equal to the probability of A times the probability of B given that A has occurred, all right, so we don't assume that the events are independent of one another, kind of like the deck of cards where you're not replacing one card before selecting another. you'd have to account for the fact that the first event occurred before evaluating the probability of the second event occurring. All right, as opposed to coins and dice, where that doesn't matter, because no matter how many times you roll a die, the probability of getting a 4, for example, is still 1 out of 6, because there's still one side on a die that has a 4 on it, and there's still 6 sides. Doesn't matter how many 4s you got in a row, the probability of getting the next 4 is still 1 out of 6. All right. But what happened here is, along the way, somebody decided, all right, well, what if we solve this for the conditional part? All right, if you solve it for probability of B given A, you get a new rule, and that is that the probability of B given A is the probability of A and B divided by the probability of A. All right. Now, in terms of the practical application of that, like I was saying before, it's pretty easy. But sometimes when you go by the numbers, it could be a little crunchy. All right. So I'll just take you through an example, because, the table is, pretty straightforward here. The table shows the results of a survey of 100 randomly selected people entering an amusement park who were asked whether they were planning on riding the Monster Loop roller coaster. All right. So pretty intimidating sounding ride. But they're asking us for the probability of getting yes as a response, given that the individual is in the age category of 16 to 25. All right. So this follows the structure of probability of B given A, which would mean, if I follow that model, we're looking for the probability that an individual is in the age 16 to 25 group, and also a yes. All right. So I would look at my table and say, okay, well, that's these 23 people. All right, those 23 people satisfy those criteria. All right, out of the grand total. Which we could figure out, but we're not going to, because you'll see in a second. All right. Then what we would want is the probability that an individual is in the ages 16 to 25 category, which would be really any of these folks, all right, whether they're yeses or nos. All right, and there is a total of 34 of those people. So if I'm looking for the probability that a person is in that category, I would say 34 out of whatever the total is for the whole table. All right. So the grand total, you could add up across the rows and the columns and get that grand total. But in a complex fraction, if your denominators are the same, they cancel out anyway. So this would amount to just 23 over 34. All right. Which actually leads you to kind of a nice shortcut, because when you look at this, you could say, all right, and sort of kind of talk to yourself about it and say, all right, the given is ages 16 to 25. All right, so ignore everything else. So focus only on the ages 16 to 25. From that group, what is the probability of being a yes? So we'd kind of parse this down to just kind of a subset of the whole table. There's 23 yeses. There's 34 people in that subcategory overall. So 23 out of 34 would get the job done.